So let us start with the work done is stretching a wire or potential energy. The next energy is potential energy, potential energy of stretched wire, of a stretched wire, right? Or the heading you may worked, or you may say it is the work done in stretching a wire, right? Both the same thing. Work done in stretching a wire. Suppose initially there is a wire, right, of length L, right? Its Young modulus is Y and the area of cross section is A. This is the area of cross section. This is A. All right. So if you suppose you apply the force and its distance become the elongation become X now. Is it clear or not? So, and you are applying the force. So now if you want to increase further, right, here if it is in equilibrium, the restoring force will be equal to what? The external force or not, which is equal to F, restoring force, restoring force, right? And if you apply the Young modulus is equal to stress upon strain. What is the strain? Say X upon L, right? So it may be written as F upon A into X into L. So here the force required to pull it, the force is nothing but YA upon L into X. So this is the force as a function of X. Is it clear or not? What does it mean? To increase the length of this wire, right? The force depends upon the elongation, right, as a function of X. So if you are doing some work, right, so you have to apply the force, and this force is variable as a function of X. Therefore, suppose if you want to further increment by delta dx, right, the dx increment is over there in this length, right? Suppose this that further increment dx. So to increase, therefore this is the force you are applying, this is the force at this position, at this point, and the further increment is delta x. So the elemental work, what is the elemental work you tell? Elemental work to increase the length, elemental length dx, dw is nothing but f into dx, the elemental work to increase the elemental length dx. So what is the total work? You have to integrate this. Is it clear or not? So what is the value of f? The value of f is y a upon L into x into dx. Is it clear or not? Initially there is no elongation, you are increasing. This is a snapshot between the initial and final. Suppose the final length become the final length, that is the delta L is the elongation. This is a snapshot between the initial and the final, right? So the value of x, that is the increment in the wire of the length, start from 0 to x is equal, what is now x? The x become delta L. Delta is the final elongation in the wire, right? So to find the total work, we have to integrate this from x is equal to 0 to x is equal to delta L. Delta L is the final elongation in the wire. Ya upon L is a constant, and this is x into dx. From 0 to dl you have to integrate. So this is Ya upon L. Integration of x is x square by 2 from 0 to delta L. Now put the limit. This is the upper limit. Ya upon L delta L square minus, then put the lower limit, it is equal to 0. All right. So it become 1 by 2 YAL into delta L whole square. Is it clear or not? You tell. So this is the total work, right? Work done in stretching a wire to length delta L from 0 to delta L, from 0 to L. This is the work done. Are you getting or not? Listen one thing. The Young modulus is nothing but the another form. This work is stored, right? This work is stored in the form of potential energy. What the work you are doing to elongate this wire, right? This work is stored, right, in the form of potential energy in the wire, right? Potential energy in the wire. So you may treat this is the potential energy divided is equal to Ya upon L into delta L square also. All right, this is the one thing. Also listen one thing, potential energy, this is the total potential energy. What is the potential energy per unit volume? Potential energy per unit volume. Whose volume is this? Because this energy is stored inside this wire. So what is the volume of the wire? The volume of the wire is A into L. So this is Ya upon L into delta L upon volume is nothing but A into L. Is it clear or not? So area will cancel out. So it become 1 upon 2 Y, Young modulus. This is the delta L square and this is L into L. It become L square. Is it clear or not? So it is equal to 1 upon Y into, what is delta L upon L? It is the strain whole square. What is strain? Strain is nothing but change in length divided by original length. This is the strain. Is it clear or not? So this is the potential energy per unit volume. The another way to write this, because the Young modulus is defined as, I'm writing this side, you can copy after this. The Young modulus is nothing but stress upon strain. All right. So the potential energy per unit volume, is 1 by 2 Young modulus stress upon strain into, this is the strain square, right? Strain square. One strain will cancel out. So it is equal to 1 by 2 stress into strain. So you will remember the potential energy. This is what? This is the potential energy and this is the volume, right? Volume. So potential energy per unit volume of the stretch wire is 1 by 2 stress into strain. You will remember in this way. Is it clear or not, you tell? Right? Copy this. So read this question. In this question, there is a steel wire of length 4 meter, right? The length of the wire is 4 meter. Stress through 2 millimeter, right? So the elongation in the wire is what? Very small, and it is equal to what? Say 2 millimeter. Is it clear or not? The area of the cross section is also given. What is the area? It is 2 millimeter square. It means 2 into 10 ki power minus 6 meter square, right? This is the area. And Young modulus of the steel is given as 2 into 10 to 11 Newton per meter square. Now the energy density of the wire. When you will do some work, the energy is stored in the form of potential energy, and the energy density. What is the energy density? You will say energy per unit volume. And what is the energy per unit volume? Say 1 by 2 stress into strain. Is it clear or not? So listen one more thing. When the Young modulus is given, here delta L is given. That is, the strain is delta L upon L is equal to 2 millimeter. This is 2 millimeter upon total length is 4. So strain is 1 by 2 into 10 ki power minus 3. The stress is not given. Stress mean the force per unit area, right? So then what will you do? You will use Young modulus is equal to stress upon strain, right? And therefore the stress become what is equal to multiply this Young modulus into strain ka strain, right? So the energy per unit volume, that is the energy density, may be written as 1 by 2, right? Stress in terms of stress, Young modulus into strain, and this is one more strain, right? So the formula may be written as 1 by 2 y into strain whole square, right? So the Young modulus is given as 2 into 10 to the power 11. What is the strain? The strain I have found, delta L upon L is equal to 1.2 minus 3 whole square. Fine. This is the strain. This is the Young modulus. So 2 will cancel out. 10 to the power 11. 1 by 4 into minus 6. So the energy per unit volume, right, is equal to, it is 1 by 4 into 10 to the power 5 joule per meter cube. It is 0.25 into 10 to the power 5 is equal to 2.5 into 10 to the power 4 joule per meter cube is the energy per unit volume, which is nothing but energy density. All right. And in the second part, what they are asking, the energy, elastic potential energy. Potential energy is nothing but E, they are asking. So E is multiply, E is equal to 2.5, the energy density multiplied by volume. And what is the volume? 2.5 into 10 to the power 4. Volume is nothing but area into L, right? So what is the area? The area is given as 2 into 10 to the power minus 6. What is the length? Length is given as the 4 meter. So how much? It is 5 5 20 into 10 to the power minus 2. It is 0.2 joule is the correct answer, right? So the energy stored is nothing but E is equal to 0.20 joule. All right, copy this. So read this question. In this question, the x longitudinal strain is produced in a wire of Young modulus y. Strain is what? Longitudinal strain is x. The Young modulus is what? Young's modulus is y, right? Young's modulus. So the energy stored in the material per unit volume. So energy stored per unit volume is what? 1 by 2 stress into strain, right? But Young modulus is given. So what is the Young modulus? Is equal to, say, stress upon strain. The strain is given as x. So in place of stress, what will you write? Y into strain, right? So 1 by 2, in place of stress, I will put the y into strain, and this is equal to strain. Fine, strain. So answer is 1 by 2 y into strain square. The strain is nothing but x. So 1 by 2 into x square. So this is the energy density, or you can say energy per unit volume. So the D option is the correct option, right? Copy this. So read this question. In this question, we have a metallic rod, right? This is the metallic rod, and this metallic rod is rotating about this axis with angular velocity omega, right? The length of this rod, the length is 0.5 meter, all right? And the radius mean this is the area of cross section. So the radius is given like this. So its radius is given as 0.1 meter, and it rotates with angular velocity omega, and it is 400. Omega is given as 400 radian per second. Fine. About a vertical axis passing through its one end, right? Calculate the tension in the rod. Listen one thing. When suppose if it is a mass m and the massless string is over there, right? So what is the tension in this string using the circular motion, right? It is mr omega square or not? So tension is nothing but mr omega square, if you remember. All right, tension is equal to r omega square. So in the first part, they're asking the tension. In the circular motion, when we have done this type of question, this string was massless and the point mass m was rotating in the circular. All right. So now we have to find the tension, right? Suppose at distance x, you consider the element dx, right? The width of this element is dx and the mass of this element is dm, right? The tension will be varying along the rod. Here this was the massless string and tension is uniform, but if you consider the elemental portion over here of the width dx, the mass is dm, so it is rotating like this in a circular path, right, with the angular velocity omega, right? So what to do? Suppose this side the tension is what? The T, and when you are moving from end to the this point, right, the point of hinge, right, so the tension is increasing. Is it clear or not? So if there is a tension T, so what to do? The because of this tension T, right, the it is rotating with angular velocity. It is rotating with angular velocity, and this is the T, right? And this T is nothing but, listen one thing, wait for 1 minute. Suppose the tension is T over here, and after dx distance, this side, the tension become T plus dt. Is it clear or not? This is T, so T is acting this side and T plus dt is acting this side. Is it clear or not? So you tell me, if this is x, right, this is x, so x is equal to x is, if you assume this is the x, wait for 1 minute, here the r is taken from this side, this is x, this is t dt, so the net force is acting this side from left to right. So what is the distance? The distance x is taken from this end. This is the distance r is taken from here. No problem. You may write the distance x from here, right? So this distance is what? Say L minus x. So it is rotating. It is rotating in a circular path, and the radius is what? Say L minus x, right? So what is the net force toward the center? Net force towards center. Please tell. Net force toward the center. It is T plus dt and T. So tt will cancel out, only dt will provide the required centripetal force. And what is the required centripetal force? Is equal to dm r omega square. Dm r omega square. What is the radius? The radius of this circle is L minus x. All right. So now what is the dm? The dm mass may be written as, by unitary method, m upon L. The mass is distributed, total mass is distributed over the length L. So for dx distance, we can write the dm mass. So here the dt is nothing but m upon L into dx, and L minus x omega square. Is it clear or not? Now we can find the differential equation n in T. This is m omega square L. This is L minus x into dx. Is it clear or not? So from this end, as a function of x, you can find the tension, right? So if you integrate this, m omega square L, integrate L minus x into dx, right? So varies from 0 to any point. Listen one thing, if you want to find the if you want to find the tension, suppose this is the rod, this is the rod, and you want to find the tension as a function of r. So at this point, if you want to find the tension, so here at x is equal to 0, and what is this? this is the this distance is nothing but what? L minus r. So from x is equal to 0 to distance is L minus r. Is it clear or not? One thing you may write, the distance you can take from here to here, right? If you assume, wait for 1 minute. If you assume this is to be x from this side, right? And this elemental distance is dx, right? So this time is t plus dt, and this, the tension is decreasing. So you may assume this is the x. Are you getting or not? The x is the distance from its axis. All right. So the same thing will be there, but the radius will be x into omega square. Is it clear or not? So it will be x into omega. So no big difference, right? The x distance you take from center of the circle, right? So now m upon L into x, this is x into x. Is it clear or not, you tell? So now the tension from here to here you have to find, right? So what is the tension at 0 as a function of x? Wait for 1 minute. The tension in the rod at a distance r, at distance L. Listen one thing. At x is equal to 0, the tension is maximum, right? Tension is maximum. And at x is equal to r, the tension is 0. So what is the tension is written? dm r omega square a r. What is the tension? Yeah, at this point the tension will be maximum over here. From r to L. Okay. At x is equal to x, the tension is T, and x is equal to L, the tension they have taken 0, right? At x is equal, they are not differentiating, they are not integrating from 0 to L, because we know the tension at this point. At x is equal to L, what is the tension? Tension is 0 because there is no mass present this side. The tension is maximum at this point. So at x is equal to L, they have tension taken 0, and x is equal to x. At distance x, the tension is T. So now if you integrate, this is T from 0, this is m omega square L, the integration of x square by 2 from x to L, right? So 0 minus T, right? 0 minus T is equal to m omega square L upon L square by 2 minus x square by 2, right? So this is the tension T. Also there is one more thing. As you are decreasing, you are changing the x, the tension is decreasing, so minus dt will also come over here, minus dt will also come, right? So minus t, and this it become t, it is m omega square by L square minus x square by 2. So tension as a function become 1 by 2 m omega square L square minus x square. Is it clear or not, you tell? M omega square, right? And what is given in the question? The m radius, the length rod, mass is not given, and the density of the material is given. So the mass of the rod, although this is the formula for the tension, right, in the rod as a function of x, in place of mass, because the mass of the rod is not given, volume into density, area into length L, right, into density, this is the mass. So A into L into density upon 2L omega square, L square minus x square. L will cancel out 1 by 2. So this is equal to rho A, rho A omega square by 2 L square minus x square. So this is the tension in the rod as a function of x. Listen one thing. At x is equal to 0, x is equal to 0. What is the tension? The tension is maximum, and the tension is A rho omega square L square minus 2, right? A minus 0. So it become A rho A omega square L square by 2. This is the maximum tension. And if you put x is equal to L, that is at this one end, the tension become what? Rho A omega square by 2 L square minus L square, L square minus L square. Fine. It is 0. So this is the minimum tension here, and this is the maximum tension at one end. Is it clear or not? Right. Copy this. So listen one thing. We will see the another method. I think you are confused. You may be confused with this, or you understand. Please tell. Varsha. Yes. It is also necessary, but in some other way, I want to explain this, right? Because it is the question not from elasticity, rather it is a question of Newton's laws of motion, right? So tell me, if this is the mass m, right, and it is rotating with angular velocity omega in the radius, suppose the length is L. The mass is the point mass. Can you find the tension here? Yes. The tension is nothing but, tell me, ml omega square, right? The net force toward the center will provide the required centripetal force. But in place of this point mass, suppose there is a rod, right? And this rod of mass m and length L, right? This is the length L, is rotating about this axis with angular velocity omega. So if you consider now, if you consider this the small rod, suppose it is connected by the small string over here, right? So I want to ask the tension at this point, right? So if you consider the total rod, its center of mass is placed at this point, and the average distance of the center of mass of the rod is L by 2, right? If you make the free body diagram, for example, if you make the free body diagram of this, the tension is acting in this direction. So this tension is providing the required centripetal force. In the same way, if you consider this is the rod, right, whose center of mass is rotating in this circle, right, and the tension will be the T at this point. What is the net force acting on this center of mass along this direction? This is the T at this point, right? So this T is nothing but, right, the radius is what? Say L by 2. So mr omega square. In place of r, what is L by 2 omega square? So this is the maximum tension, right? ml omega square by 2 over here, right? If you put x is equal to 0 over here, right, x is equal to 0, so the same thing you will get 1 by 2 m ll will cancel out, ml omega square. So the maximum tension, this is the maximum tension, right, in terms of m, if you consider. So the maximum tension at this point will be ml by 2 omega square. Is it clear or not at this point, right? At this point. But if they want to ask the tension at some other point, then what to do? Listen one thing. First copy this, then I will explain. So this is the tension at one end. All right, tension at one end. Now, if you want to find the tension at some other point, for example, if this is the rod, right, the rod of length L, the mass m, it is rotating about this axis, and you want to find the tension at distance x what is the tension at this point? Is it clear or not? So this tension as a function of x, we are going to find. So how to do that? Right? How to find this tension? Listen. To find the tension, this, suppose here the tension we want to find. So you can consider that there is a string, a small string is over there, right? And because of this small string is connected between the two parts, right? Suppose this is the x distance. Here the tension in this string as a function of x you want to find, right? So if you consider this is the portion of the L minus x distance, fine, its mass can be assumed to be m dash. So you will consider that it is the small portion is the m dash, right? And this is the tension which we have to find, right? And because of this tension, it is rotating in the circular path. Are you getting or not? So suppose this is the t dash, suppose this is the t dash. The t was here, which we have found. So this t dash will provide the required centripetal force. T dash will provide required centripetal force. Are you getting or not? So what is the t dash? Say m dash r omega square. What is the r? The center of mass of this portion will be at the m dash, so it will be the radius. This is the radius. So what is this radius? Can you find? Yes, we can find. Up to this, the distance is x, and this distance is what? Say L minus x. So what is this distance? This is the center of mass m dash. So if it is L minus x, what is this distance you tell? L minus x by 2. Are you getting? So what is the radius over here? The radius is nothing but x plus L minus x by 2. So the radius is 2x plus L minus x by 2 is equal to L plus x by 2. So in place of radius, right, I will put L plus x by 2 into omega square. Is it clear or not? And what is the m dash? M dash is the portion of the length L minus x. So for length L, the mass is m. For 1 meter, m by L. What is the distance, this portion? L minus x. The mass will be m upon L into L minus x. So m dash is m upon L into L minus x. So the value of m dash will be written as m upon L into L minus x. Is it clear or not? So this is the tension. A 12 m L minus x L plus x whole square. So this is 1 by 2, right? M omega square L square minus x square upon L. So this is the tension as a function of x, you can say. Are you getting or not? At this point, the tension we have found, which is same as, which could be found with the help of the integration. All right. So you tell me, this is the general expression. The tension is, as the x is increasing from center, the tension is decreasing. So can you tell at x is equal to 0, the tension is maximum. And what is the maximum tension you tell? M omega square upon 2L L square minus x, which is equal to m omega square L upon 2. And x is equal to capital L. It means at one end the tension is minimum. And how much it is? L square minus L square. L square minus L square upon 2L. The minimum tension is 0. The maximum tension is this. Is it clear or not? So basically, without integration we have found, right? Using the integration, the same expression we have found for the tension, or without integration here, we can find the tension. Although this is correct and this is also correct, right? Copy this. So we have found the tension as a function of x. Although the mass is not given in this question, in place of mass, its volume, its area, length and rho is given. So in place of mass, we can substitute AL rho, LL will cancel out. So this may be the expression for the tension as a function of x, right? Listen one thing. Although this is the portion is of NLM, right, which should be covered in LNM. Now, the elongation of the rod. Listen one thing. If this rod was at rest like this, so its length is L. Now, because of rotation, the tension is produced at every point. Is it clear or not? You tell. So every portion, if you consider of this rod, if it is start rotating, right, comes under tension. Is it clear or not? Comes under you are not applying the force, rather because of the centrifugal force or because of rotation, you can say every part comes under the tension, and also the tension is not uniform. Listen, if it was the rod, right, and you apply the force, so you can easily write the elongation in the rod. Are you getting or not? Because here the force is what? Is constant. But in this case, when it is rotating, the force is variable. So to find the total elongation in this rod, what you have to do? You have to use the integration, right? Or you have to use the help of the calculus. For that, we cannot write the total elongation in the rod instantaneously. What we can do? We will choose a small portion of width is dx, right? The mass is dm, and this portion is under tension. You understand? What is the tension at this point? This portion is under tension. Please tell me, what is the tension at this point? This is the tension, right? This is the tension. So if this portion is under the tension T, so there will be some elongation or not? Yes. How? Young modulus is equal to stress upon strain. When the tension is produced, suppose the strain is dy. So what is the original length? Say dx. What is the increment? Small increment. Say dy. So stress, Young modulus is nothing but stress upon strain. I am writing this expression for this elemental part. The original length is dx. Because of tension, when it comes under the tension T, so the elongation is delta y. So stress is T upon A, strain is dy upon dx, which may be written as T upon A dy into dx. So dy is equal to T upon ya into dx. What is dy? Elemental increment, right? Elemental elongation in the elemental part dx, right? So to find the total elongation, what you have to do? You have to integrate this from x is equal to 0, because these type of the elements start from x is equal to 0, then this is the another element, this is the final element, right? From 0 to L you have to integrate. So this is ya. What is the value of t? The t value is m omega square 2l. This is L square minus, I am writing this side, delta L is equal to 1 upon ya. What is the value of tension? M omega square upon 2l. L square minus x square into dx from 0 to L, because we have to find the elongation at every portion from 0 to L. So m omega square, right, 2yal. This is 0 to L, L square minus x square into dx. So I am writing the integration. What is the integration of L square? Say Lx minus x की power 3 upon from 0 to L. Is it clear or not? So in this way, you can find the total elongation in the rod. This is the delta L m omega square 2 yal. Haji, put L. So it become L cube minus L cube upon 3. And when you will put 0, it becomes 0. So it become, this will become 2L cube by 3. Right. So m omega, what is m? M is the mass of the rod. So mass of the rod is volume into density into omega square upon 2yal. The mass I have replaced with al into rho, and this side 2L cube upon 3. Right. So yal, al will cancel out. 2. So this is 1 upon 3. 2 will also cancel out. Rho omega square L cube upon y. So this is the elongation in the rod, right? So what is the option? What is the elongation? The elongation is rho omega square L cube y. Now you can put the value. What is the density? 10 to the 4. What is the omega? 400. What is the length? Say 0.5 का cube upon Young modulus 2 into 10 की power 11. So the total elongation we can find when you will calculate minus 3 meter. It is 1 upon 3 millimeter is the total elongation. All right, copy this. So read this question. In this question, you have to find the elongation in the block. If the mass, this is the block, right? The force F is applied over this area, right? The area is what? Say A, you can think, and the mass is M, and there is no friction over here. It is smooth. The length of this block may be assumed to L, right? And area of Young modulus is Y, you can think. Is it clear or not? So you have to find the elongation. Listen, one more thing. This is very much similar to the previous problem. Suppose this is the cross, this is the side view. Although this is the 3D diagram, if this is the force, listen one thing. If this was of the length L, the force you applied, right, it is placed over here. Fine, it is fixed. Suppose it is not fixed, right? It is the mass M, it is moving with some acceleration A. And what is the acceleration? Say F upon M, but it is fixed. If you apply the force F, what will happen? Tell me. So every point of this material comes under the same tension F. So what is the delta L you will find? How to find? Young modulus is equal to stress upon strain. The area you can assume to be the A, right? This area is what? A, and this is the force F. The force delta L upon L. So F upon A, delta L into L into Y. So delta L is FL upon YA. Is it clear or not, you tell? So this is the elongation you can write, Varsha, or not, you tell? But here every point is under the same tension, same force, right? Because they are connected in series. Is it clear or not, you tell? Right. If you make the free body diagram, right, here will be also the force F, right? That is why it is at rest. So everywhere the force is F, but in this case, if you consider a portion X, suppose this is the mass M, a portion at a distance X, can you write down the tension at this point? This question we have done in the NLM. What is that? Suppose this is the rod of mass M, right, length L, The force F is applied, placed on the smooth horizontal plane. Find the tension as a function of x. Please tell how to find the tension as a function of x. Listen, to find the tension, you can think there is a small rope or string connected between the two parts, as we have done in the previous case. Although the acceleration of this portion is rod is what? F upon m. Is it clear or not? So if this is L, what is this portion? Say L minus x. Suppose the tension over is T. So because of tension, this mass m dash is moving in horizontal direction or not? Because of the tension is this portion. The tension between this two portion, right? This is the m dash portion. If it is moving towards right, make the free body diagram of this portion. It is moving to right with the acceleration a. So what is the force acting upon this portion which is taking it into the forward direction? The tension applied by this portion on this portion. That is why it is moving. So now you may write F net is equal to what? Is equal to m dash into a. What is F net? Only the tension. What is the m dash? The m dash may be written as by the unitary method. How? For the length L, the mass is m. For 1 meter, mass is m by l. What is the length of this portion? Please tell. L minus x upon L into L minus x. So what is the m dash? The mass of this portion. Is it clear or not? So the tension is equal to m upon L into L minus x. And what is the acceleration we have found? Acceleration is common for both part, this part and this part, is equal to F by m. So the tension is F upon L into L minus x as a function of x. Is it clear or not, you tell? So it means if this is the block or the rod of length L moving under the force F, every portion is under different tension, which varies according to this. In NLM, they ask the tension at the midpoint, tension at this portion. So for different x, you can find the tension in this rod. For example, at x is equal to 0. What is the tension at x is equal to 0? You tell. 0, F upon L, L minus x, L minus 0, L will cancel out F. So the tension at this point is what? Say F. At x is equal to L, at this end, what is the tension? Say 0. At midpoint, what is the tension at midpoint? You tell. Put x value is equal to L by 2. F upon L, L minus L by 2. So it is F into L by 2 is equal to F by 2. You are getting this thing or not, you tell? Right. So first objective is to find the tension as a function of x in this bar to find the total elongation, right? First copy this. So now how to find the elongation? Tell me how to find the elongation. Then again you will consider at distance x the small portion of with dx. This is the dx, right? The mass is dm. So this portion is under tension or not? Yes, this is portion under tension. If it's initial, when the no force is applied, it will remain dx. When the force is applied, so it comes under tension and there is some elongation in this portion and it becomes dx plus dy. So what is the strain developed? Say dy upon dx. dy is the elongation in the elemental part dx. What is the stress over here, you tell? Say the tension at this is T given by this tension upon here. So what is the Young modulus? Stress upon strain T upon A dy upon dx. So T upon A into dy into dx. So dy come this side, T upon A into y into dx. So this is the elemental elongation, elemental elongation in elemental part dx. In this part, this is the elemental elongation. So there are so many parts. Every part is under different tension. So to find the total elongation because of this tension, what you have to do? You have to integrate this, right? So to find the total elongation, you have to integrate this, and this is equal to t upon ay into dx. 1 upon a into y it is. What is the tension? It is f upon l, l minus x into dx, and the x varies from the element start from 0 to x is equal to l, 0 to l. So it is 1 upon ay. The f upon l comes out from integration. This is l minus x into dx from 0 to l. F upon yal, lx minus x square by 2 from 0 to l is equal to f upon yal. Put the upper limit, l into l square by 2 minus 0. Fine. So this is equal to f upon yal is equal to l square by 2. Fl upon 2ya. So this is the total elongation in the rod when a force F is applied. The small parts are are under different tension. So you first write for the small part, for the small elongation, and then this is the small elongation. You will integrate, you will get the total elongation in this rod. All right, copy this.